Hey everyone, this is Dr. Walker. This is the guided examples video from video 237, resistors in parallel. In this video, we're actually going to do an example that puts together resistors in parallel and resistors in series. So we're going to have a circuit that we're going to be simplifying and also working backwards to find the unknown information. Let's take a look at this problem. There are 4 parts to it. The first part is to find the equivalent resistance of the circuit. So we're going to have to redraw the circuit after every step. We have to identify what's in series, what's in parallel. I like to always label my resistors, so let's call this R1 and this R2 and the one on the right R3. So first step is redraw your circuit, simplifying a set of resistors. So I want you to think which ones are you going to simplify? So hopefully you said R2 and R3 because they're in parallel. So you simplify R2 and R3 into an equivalent resistor and you leave R1 where it is. So we're going to have R23 is the equivalent resistance of R2 and R3. The next step can be either to do one more simplification or first go ahead and calculate the resistance that you just drew, the R23. And I usually like to go ahead and calculate it. That way I don't forget where this R23 came from. It came from 2 and 3, both of which were in parallel to get to R23. So I'm going to go right below this circuit and calculate that equivalent resistance R23. For parallel, we use the 1 over equation. So 1 over R23 equals 1 over R2 plus 1 over R3. Both of these resistors have a resistance of 10 ohms. So 1 over 10 ohms plus 1 over 10 ohms. That's going to give us 2 over 10 ohms. And then to get R23, we have to flip both fractions. So R23 equals 10 over 2, or 5 ohms. And just a reminder that when using the 1 over equation, if the two resistors that you are simplifying have the same exact value, then the equivalent resistance will be half of that, and you don't have to go through this. You can just remember that when you're using the 1 over equation, you got 2 resistors that are identical. The equivalent resistance will be half of one of those resistances. And now we're going to simplify the circuit one more time. So see if you can simplify it and calculate the equivalent resistance by yourself. And then unpause the video and let's take a look. We have 2 resistors in series now. They are directly connected here with just one wire. There's only one path for the charges to flow here. So we have one equivalent resistor. We can call it R equivalent, or we can call it R123, doesn't matter. And that's what this first part here is asking us for. So when you're in series, both of these were in series to get to R equivalent, then you know that the resistances add up. So R equivalent equals R1 plus R23. That's going to give us 5 plus 5, which is going to give us 10 ohms as our equivalent resistance. Okay, so that was the first part. The next part is what is the current supplied by the battery in the circuit? So when we are given the original circuit here, it's hard to know, well, how much current is flowing out, because we know that the current depends on the total resistance. But now we have the total resistance, the equivalent resistance. So now we can use the simplified circuit to find the current using Ohm's law. I is delta V over R equivalent. That's going to give us the current flowing out of the battery here and through that R equivalent. So the voltage is 10 volts over 10 ohms. is going to give us 1 amp for the current supplied by the battery. So if that current is leaving the battery here in this simplified circuit, then that same current is going to be leaving the battery no matter which circuit that you're looking at. Now we want to know what is the current through each 10 ohm resistor. So this is a case of working backwards. We know the current through the equivalent resistor, and we know that R23 and R1 were in series to get to our equivalent. When resistors are in series, we know that the current through them is the same. So when you're in series, you bring back the current. The current through the equivalent resistor is the same as the current through R1 and R23. So now we know that the current, I'll call it I23, the current through R23 is equal to 1 amp. It's equal to I. Now that we know the current through R23, we can find the voltage across R23. So you see how we're working backwards. When working backwards, we want to know all three of these variables, delta V, I, and R. So let's do it here. Kind of ran out of room a little bit here. Got a little bit extra room. So let's find the voltage across resistor 23. If you manipulate Ohm's law, I is delta V over R, then you know that delta V equals I times R. So to find a voltage across 23, it's going to be I23 times R23. I23 is 1, R23 is 5. So 1 times 5 is 5 volts. Okay, we're almost done. Just to recap, we had the simplified circuit, we found the current. We brought the current back because the resistors were in series. Once we had the current, then we could now solve for the other unknown variable, which was V. We found delta V across R23. We have all three variables dealing with the resistor that we care about, R23, because R23 will lead us back to numbers 2 and 3. So now we're ready to go back again. When two resistors are in parallel, we know that they have the same voltage as the voltage across the equivalent resistor. Right? Series, you have current. Parallel, you have voltage. That's the same. So if we're looking at either of these resistors, let's say resistor number 2, if we want to find V2, the voltage across resistor 2, that would be the V23 that we just found. That would be 5 volts. So now that we know the voltage across resistor 2, we can find the current across resistor 2. Right? Whenever we know either voltage or current, we can find the unknown, which is either current or voltage. So the current through R2 is delta V2 over R2, which is 5 volts, and R2 is 10 ohms. So I2 is equal to 1/2 amps. You can use the same process to find a current through R3. You have the same voltage that you had on V23, you have the same resistance. So the current through I3 is also 1/2 amps. Okay, so we are done with B and C. Now, what is the current through the 5 ohm resistor? So the easiest way to do this is to look at this middle circuit here. The 5 ohm resistor is R1. We know that the current through our equivalent resistor here is the same as the current through R1 and R23 because they were in series. So when we found the current supplied by the battery, when we found 1 amp, that is also equal to I1, the current through the 5 ohm resistor. So we just went through a lot of math, but one thing that I would like to say is that you could have done this without so much work by just kind of looking at it and reasoning through it. But it's really good to be able to do this kind of work because sometimes the numbers aren't going to work out this nicely. But what I mean as far as kind of reasoning through it, once you know, for example, that these two 10 ohm resistors simplify to one 5 ohm resistor, and you consider this middle circuit here, then if you have 10 volts from the battery, and you have two resistors that are the same, they're both 5 ohm resistors, they're identical resistors, then you know that the voltage across them is going to have to be the same, and it's going to have to add up to the 10 volts supplied by the battery. So by looking at this circuit right here, you could have already deduced that delta V was going to be 5 volts for both of these resistors. And you could have just looked at this circuit and seen that, hey, if we have 1 amp coming out of the battery, well, they're all in series. We have that 1 amp going through R1. The current going into the battery is the same as the current leaving the battery. And finally, as far as how we could have figured out that we had 1/2 amp of current going through these two, well, once we know that we have 1 amp here going to the right coming out of the battery, we know that these two 10 ohm resistors are identical, so we know that the current splits up when it reaches a junction here. So if it has 1 amp here and it's going to split up evenly because they're both identical resistors, then it's going to split up into 1/2 amp for R2 and 1/2 amp for R3. So I really encourage you to go through this problem again by yourself, just because it is a long process to do all the math, but it's good to be able to do it for when the numbers don't work out so nicely that you really need the equations to help you figure out the answers.